Next up, we have TenseFlatables, 3D printed tensegrity-assisted inflatable structures for manufacturing and materials category. Please welcome William Johnston and Dr. Bhisham Sharma.
I think you're fine. Thanks.
All right, thank you everyone, and good afternoon. I'm William Johnston, and I'm a PhD student and an NSF Graduate Research Fellow at Michigan Technological University.
And I'm Bhisham Sharma. I'm an associate professor at Michigan Tech University and also his PhD advisor. Our topic today is going to be TenseFlatables, advanced inflatables for a sustainable future. So the story of humanity basically is our desire, our need to shape our environment. Right? We started with trying to replicate our cave dwellings with the materials at hand, started construction using the techniques that we had. As we learned more about manufacturing, we learned more about materials, we learned more techniques, more structural mechanics. We managed to make more complicated structures. Colosseums, more complex, large, also beautiful churches, for example. Our initial focus was mostly on making larger things and more complicated things. As we learned more about new materials, new manufacturing methods, we were able to come up with even more complicated structures, right? But over the last few years, or rather the last century, our focus has changed more from complexity and largeness to more complexity, but more lightweightness, right? There's two main reasons for that. The first reason is the developments in aerospace engineering. The things that we want to fly, they need to be lightweight. So lightweightness is kind of important for that. And the other thing is climate change, right? So climate change is focusing us a lot more on making things lightweight. We need things to be lighter so that they consume lesser amount of fuel, right? So our focus has moved on more towards complexity and making things lighter. But from any reports, if you pick up a newspaper, you know that whatever we are doing right now, it's not really working as well as we would hope. For a more sustainable future, we need more creative ideas. We need more radical solutions, right? So one creative idea, one radical solution which we came up with was, how about we just get rid of all the solid part? Can we just have a structure which has the shape that we desire and which also retains the mechanical performance that we are requiring, right? So basically what I'm describing is an inflatable material, right? So in an inflatable, you have a thin membrane. You use the membrane to achieve the shape that you want. You fill the membrane up, keep it airtight, and the pressurized air inside it, that's going to be the load-bearing component. So basically, you're replacing the solid with the air, and you're retaining the shape using the inflatable material, right? So if inflatables are so great, they are so lightweight, why don't we really use them for engineering applications? Most of the applications for inflatables right now are really entertainment purposes, right? For parades, we'll have a big parade later on this month outside, right? So we'll see a lot of inflatables out there. For entertainment applications, for children's birthday parties, balloons, those kind of things, that's what we use inflatables for right now, not really for engineering, right? There are two main reasons for that. The first reason is that it's very difficult to get dimensionally tolerant inflatable shapes, right? The process itself involves you take 2D shapes, you cut them, and then you glue them together, and then you inflate the whole thing. That kind of makes it very difficult to achieve dimensional tolerance and very precision, right? So engineering is all about precision. If you can't have precise structures, you can't really use them for critical load-bearing applications and engineering applications. The other part is it's surprisingly difficult to actually manufacture inflatables. You need to start from the 3D shape that you want, work backwards, which is called the form finding process, and you identify, okay, what are the 2D shapes that I need to cut out? How do I glue them properly so that in the end, when I inflate it, it's going to achieve the 3D shape that I need, right? So those two things are kind of a big hurdle in using inflatables for engineering applications, right? So our solution basically addresses those two versions. How does it address it?
Yeah. That's a good question. So to address these current limitations, we look to revolutionize the way we look at inflatable structures. So our solution is TenseFlatables, the first 3D printed tensegrity-assisted inflatable structures. And TenseFlatables revolves around two key components, an external airtight geometry and an internal fibrous mesh that revolves around the concept of tensegrity. And what tensegrity is that when you inflate the structure, what happens is that the inner tensegrity mesh actually resists tension, which allows it to keep its shape as it's inflated. But when it's deflated, it allows compression, which allows us to kind of fold away and store the object like a typical inflatable would. And so the secret behind our process is our actual innovative patent-pending manufacturing process. And what this does is that we use 3D printing to basically customize nearly every aspect of the TenseFlatable structure. So we can change how the fibrous tensegrity mesh on the inside is oriented, the fiber thickness, the fiber density, the fiber orientation, and all of this really helps to keep the inflatable shape. And so because of this, we can produce a bunch of different types of inflatable structures, like those with complex curves and external or internal features. But most importantly, what TenseFlatables can do is create flat surfaces and sharp corners that you definitely would not be able to see in current inflatable techniques. And so because of this, our method allows us to have scalability because we use just existing FDM infrastructure, which is just basic 3D printing that you can find on Amazon, really, those 3D printers. And also we can use any type of material that's able to be extruded through traditional 3D printing techniques. That could be basic plastics all the way up to more advanced metals. So you may be wondering, why specifically do we want to use 3D printing? Essentially, as we mentioned before, one of the main issues with current limitations of inflatable structures is the difficulty of doing the form finding procedure. But with 3D printing, we don't have to worry about form finding at all because it's already a 3D printed object. And so to kind of facilitate this idea, we came up with a proprietary algorithm that will take any input file as any solid 3D object file, like an STL file or anything that you can scan with a 3D scanner and turn into a digital file. And the algorithm will turn that into a TenseFlatable file that's ready to be sent to any standard desktop printer. And because of this, we're able to TenseFlatableize really any type of structure, like the Empire State Building. If you'd want to do that, you're able to do that, or an SAE logo, or even a rocket. And so in addition to lightweighting any solid object, what we can do is we obviously can solve those form finding issues, and we're able to automatically produce complex shapes with controlled local deformation characteristics as well. So really, with the TenseFlatablization algorithm, we can turn any solid object into a TenseFlatable for a bunch of different applications.
So to summarize, basically our method, our manufacturing method allows us to start with any solid 3D shape. We can convert it into an equivalent TenseFlatable object. And we are also able to control the internal tensegrity mesh so that we can achieve as much dimensional precision as we want and also tailor the local deformation characteristics. Right, so that kind of opens up this technology for multiple applications. Some applications for the automotive industry, we could have dynamic steering wheels with adjustable grips. Another one could be next generation safe airbags, where maybe we replace the car components, the steering wheel itself with a TenseFlatable component, right? So that adds some security, some protection for the passenger. The most obvious one is space, right? Deployable modules. We can have things which we print over here, take them to space, and then deploy them into the shapes and for whatever load applications that we need up there. We are aerospace engineers, so that's primarily our focus. Aerospace engineering, the main need is to reduce the fuel consumption of aircrafts. So we can 3D print TenseFlatable aerospace components as well. Electronics, we could, since we are relying on 3D printing, there are two options there. We could either print using conductive filaments, or we can actually design our objects such that we are 3D printing in such a way that we can integrate sensors within it, right? Or we can also have for safety applications where we can design vests or clothing where older people or people who are more prone to falling down, they could have something where there's a sensing element. As they fall, maybe it inflates and protects them. Right, for biomedical applications, this is something that we are quite excited about as well. Currently for surgical procedures, they also use inflatable balloons to be able to open up vessels. Right now, they just expand out completely because they are simple inflatables. That causes a lot of secondary trauma to the tissue surrounding it. Right, so maybe we can overcome those kind of things by controlling the shape of the TenseFlatables. Robotics, maybe we can print really good grippers for some of the pipe repair applications. And also, we can also go down the fashion route. If somebody wants to 3D print their own bags, for example, you want to protect your iPhones, your iPads, you can 3D print your bags, put everything in there. If you have an accident, if you fall off your bike, your devices are still protected. Right, so there's multiple applications. Essentially, if there is a structure, we can ideally replace it with a TenseFlatable. That's the end goal. Right, so the main technology is that we can 3D print lightweight, scalable, and deployable structures in a variety of categories. Our end goal, essentially, is to reduce weight as a means towards sustainability. Right, and we need new ideas, we need creative ideas for a greener future, and we believe that this could be one of those ideas. So, thank you very much.
Questions?
Thanks. Is there any post-processing required after the parts come out of the 3D printer?
No. And that is part of our focus, that we wanted to keep the manufacturing process as simple as possible so that we can fabricate complex shapes that do not require post-processing, so that we have an entire streamlined workflow for printing, right? So the trick there is making sure that the 3D printing process parameters are such that we end up with airtight filaments.
Do you have a resolution limit for the printing process?
No. So it all depends on the 3D printing method that we are using, which is basically an extrusion-based method. So we can go very, very high resolution. That depends on the material that you're using, right? So the capillary effects as you're extruding from the nozzle, that might affect things, but that is different for every single material. And on the larger scale, with 3D printing, with extrusion-based, people are also printing houses at the scale. So we can also print very, very large structures as well.
Do you think that limitations in the materials behavior that is required for 3D printing is going to impose limitations on the application?
I don't think so. Because primarily right now, there's a lot of work going on 3D printing, on additive manufacturing in general, and the field is moving on very, very quickly. So there are new and new materials coming out which you can use for 3D printing. For example, recently we can start printing with conductive filaments. The work that we have done over here that is using TPU filaments, which are flexible filaments. We have started exploring the use of metal filaments as well. So the material space is increasing more and more. So we expect that to help our case.
No more questions then, Thank you.